All right, so last week before the long weekend, we talked about doing checksums for error detection, right? So then I said left off the hand, it's like, well, right off the bat, we had brought up as a class that CRC was probably better. And so we're actually going to talk about what a CRC is today. We'll go through something a really simple CRC, granted that computers are really good at math, and they don't really care about large math problems, particularly if they're in the 32-bit space, or with modern computers, 64-bit space. It really doesn't matter. Every math problem from 1 minus 1 to in a 64-bit computer, right? Several hundred billions minus several hundred bits. It's all the same math problem to them, so it doesn't matter. So, but we'll give you an idea of what a CRC does, how it actually works, and then we'll talk about the security, or not the security part, but the error protection part of properties of CRC, and we'll find that they're a lot better than checksum. And then we'll move on to error correction. And then hopefully we'll cover actual retransmission, right? So error detection doesn't do you much good right now, other than to tell you, hey, say this packet or whatever you're doing the detection on is bad, you need to send it again. So we'll talk about how retransmissions actually work. And we'll revisit retransmissions in depth when we get to the transport layer, but we'll discuss them a little bit now. So let's talk about CRC. So in simpler terms, let's think about, we want to send the 3 bytes 302, and we want to send that across the network. Granted, we're using small numbers here because we're humans again, but computers can do much larger numbers, right? It's not a problem for them. And we want to be able to send that and have an error detection scheme. So I propose this. We're going to say every code word that we send, remember a code word is both the data and the check bits, so every code word we send has to be evenly divisible by 3, right? So we're going to put a check bit here, and for right now let's just say this is 0, and we're going to make 3020 evenly divisible by 3. So what does the check bit need to be?
1.
It needs to be 1, right? So we could go through, it's like, well, 3000 is evenly divisible by 3, but in 20, you can get 18, so if it was 21, then it would be evenly divisible by 3. Turns out there's some tricks in math that you can just add all the digits together, and that has to be evenly divisible by 3. So 3 plus 2 plus 1 is evenly divisible by 3, so 3021 is evenly divisible by 3. And we could just send that code word. And then on the other end, we simply ensure that this number that we received is evenly divisible by 3. If not, it's in error. So let's take a look at what we're sending here, right? So we have 1 check digit at the moment. We're going to call that K. So K equals 1. And then we have a generator. And our generator in this example is 3. Both sides agree, hey, we're going to divide this thing by 3. Obviously, they have to both have the same idea, otherwise the scheme doesn't work. So our generator, which is C, equals 3. So what we want to do is we want to do this on a much larger, and we want to do it with, so we're going to technically do it by division in here, but you can design an algorithm that's not division. Why would we not want to do real division? It takes too long, right? It's by far the longest operation in a processor is division, right? So it takes too long. So there's usually, even when you guys are writing code and you write a hard-coded division in there, the compiler will usually take that division out and do a bunch of crazy shifts and adds and subtracts and blah, 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 blah to get rid of that division if it's hard-coded in there, right? So we're going to do the long division in here, but we could see that this could be mostly done with shifts and subtractions, because that's all we're going to do is shifts and subtractions. Okay, so the catch is CRC doesn't do it on bytes this way, right? We're going to do it on bits. And we are also going to do that across with finite field arithmetic. So we're going to do bits, so everything has to be ones and zeros. And we're going to do it with a finite field arithmetic of modulo 2, which means that 0 minus 0 is 0, 1 minus 1 is 0, 1 minus 0 is 1, and 0 minus 1 is 1. So we're going to do that. So let's take a generator. And our generator in this case, because we're doing finite field arithmetic, is going to be the polynomial x to the 7th plus x to the 4th plus x to the 3rd plus 1. So this polynomial can be represented in the binary form of 1, oh actually I think, sorry, it's x to the 1st. No. So it can be represented as 1, 0, 0, 1, 1, 0, 1, 0, right? Yes. So if we were taking this as our generator now, this would be the number that both sides agree on both sides. And then you take your entire code word, well, when you're generating the CRC, you're going to divide your data by this number, and then you're going to add the remainder on so that it's now evenly divisible by this generator. Right? On the other end, we're going to take the entire thing and make sure that it's evenly divisible by the generator. Right? And so on one side we generate the check bits, on the other side we just make sure that it's clearly evenly divisible by 0. So let's run through an example with a smaller number. Let's use a generator of x to the 4th plus x to the 1st plus 1. So that's our generator. That means in binary form, what does that look like?
One zero zero one.
1, 0, 0, 1, 1, right? Now let's take the data bits, which is we're going to take the data bits 1101, zero, and then 5 ones. That's going to be our data. And we're going to divide this and then put the correct remainder in there so that it's divisible by 0. So we have this generator here. How many remainder bits are we going to need? Huh?
5.
Let's think about it. If we had 5, right, then we could actually go one step too far. So we're going to have 4, right, because really this is going to be key on where we land here. So since that one is 5, our generator is 4. So our generator is x to the 4th plus x to the 1st plus 1, which translates into binary representation as 1, 0, 0, 1, 1. That means our k bits, remember from before we had one check bit, is going to be, or one check byte or symbol last time. Our k is going to be 4 because our generator is of a length 5. Let's do the division. So remember, it's just binary, it's modulo 2 arithmetic, right? So it's really fairly simple, right? So it's 1, 0, 0, 1, 1, right? So that gives us 1, 0, 0, 1, 1. Right? And then we divide that again. 1, 0, 0, 1, 1. Hey, look at that. So all of those are zeros. So that's 1, 1, 1, 1, 0, and that's the first check bit. And then we divide again, 1, 0, 0, 1, 1. So that's 1, 1, 0, 1. And then we get another check bit. And then 1, 0, 0, 1, 1. So that's 1, 0, 0, 1. And we get another check bit. And then 1, 0, 0, 1, 1. That's nothing, 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 1, and then our check bit. And we're done. We can't divide anymore. We just pulled out our last check bit. So if we pull out our last check bit, remember, in the last one, if we would have divided it by 3, we would have got a remainder of 2, and then we would have subtracted 2 from our generator, blah, 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 blah. This is all modulo 2 arithmetic. So all we have to do is take this, because addition and subtraction are the same thing in modulo 2 arithmetic, then we simply take this right here, and we stick it up here. So now our code word becomes 11010111110010. And if you take that and you divide it by the generator on the other side, you get a remainder of 0. Because that's exactly what we calculated in the first place. And if you get a remainder of 0, then it's without error, or at least the error matters. So, obviously we just did CRC5, a version of CRC5, right? Most of the time it's CRC32, which means you have a 32-bit polynomial, and you're dividing it into a much, much, much larger code word. So then the 32 bits are appended to the end to make sure that it's evenly divisible by 32. But you notice that from a computer standpoint, all these are shifts and XORs. Right? So both shifts and XORs are super easy in a computer, 1 clock cycle, so that it can actually calculate this extremely fast. So let's take let's talk about CRC in general. So it actually takes a lot of math to figure out the properties, so we're just going to state them. So CRC32, the actual real 32, is a standard number, and it's a 32-bit polynomial starting with x to the 32nd, obviously. Actually, x to the 31st, because it goes down to x at 0. And then the Hamming distance on that is 4. So if the Hamming distance is 4, how many errors can we detect? We can detect 3 errors. So unlike internet checksums, where you could still only, there might be some other properties, right? It can only detect 1 error. internet checksum, because if you had an error that upped 1 bit and an error that subtracted 1 bit in 2 different code words, 16 bytes apart or 16 bits apart, then the checksum failed. So in some cases, internet checksum will fail with 1 error. This will not fail until there's at least 4 errors. Because this is a cyclical parity check. Essentially, we're doing XORs on this, just like we did for parity. It detects all odd number errors also, just like parity did. And it can detect bursts of up to k bits errors. So k in this case was 4, right? So in CRC 32, what's k? 31. It can detect bursts of errors up to 31.
Did you change that 1 at the second to last 0? Is that what the result was?
Yeah, so our remainder, our last check bit that we pulled down was here. We can't pull it out anymore.
Okay.
So we simply take this and stuff it up there. And then prepend the right number of zeros, right? So it turns out it's actually pretty good. CRCs are used widely in all sorts of things. Like it's used in cable modems. It's used in Wi-Fi, asynchronous DSL. It's not used in IP, TCP, UDP, general internet stuff. As far as like most of the backbone. Why? Why wouldn't we use it in TCP, IP, UDP?
Because it just detects the errors, right?
So this doesn't correct them either. This just detects errors. So remember, Hamming said that we could with it because our Hamming distance is 4. No, we still can't detect any errors. 'Cause we need at least 5. So the reason is because IP is, while not static, it can be changed, right? The change is very heavy lifting. So when we get through in TCP and UDP, you'll find that every version of TCP is backwards compatible with the old version of TCP. So even the newest versions are still backwards compatible with the oldest versions. So you can't just go out and say, hey, we're going to take this 16-bit checksum out of it and stick a 32-bit CRC checksum in it, because it would never. You'd have to come up with some crazy way to make that backwards compatible. It's not going to happen. So, but is not all is lost, because the next question is like, okay, we can do error detection. We discussed that error detection is in Wi-Fi. We've discussed that it's in IP. We've maybe not discussed, but we've hinted at that there's some error detection or error correction at the physical and data link layer, right? We're still just doing data link, right? There's error detection everywhere. So it turns out that error detection and error correction really needs to be everywhere in the whole stack. So down at the physical layer, we try to use error correction to mask errors that they're coming across the network. Try to take out all the low-hanging fruit, particularly the stuff that we can access the physical layer for, which we'll talk a little bit about today. So, because remember, sometimes we have a strong 1, sometimes we have a strong 0, and then sometimes we have a weak 1 and a weak 0, because they're all analog signals and we can measure that. It's not really binary yet. If we can measure that, then we can do a thing called bit zeroing, right? Instead of trying to use every bit as all equals, we have some bits that are more equal than others. And if we do that, it turns out we can come up with some pretty cool error correction schemes that we'll discuss. We won't go through because they're awful and super complicated. But we'll discuss a very simple example what that looks like. So we do error detection everywhere. So just because checksum is a weak error detection mechanism doesn't mean that all is lost, right? Because you can put error detection in your application layer if you want. If you're designing an app, you can put the error detection in there. Or you can put error correction in there, depending on what you want. So let's talk about error correction. Let's think about so remember Hamming said that the theoretical limit for error correction was the Hamming distance equals 2D plus 1, where D is the data bits. So if you have a little d data, right, multiply that by 2, add 1, that is your Hamming distance. So you can take your Hamming distance and reverse engineer what the data is. So for every valid code word, if you have a Hamming distance of 5, then you can have at most 2 data bits, which sounds really bad. But that actually scales fairly well. And this isn't talking about anything with when we start putting physical layer stuff in. This is just you have a code presented to you, no other information. Let's see if we can figure something out. So Hamming didn't just postulate this. He actually came up with a way that it actually works. So let's take a visualization of a set of code words. So remember I said this is your field of possible code words with just random bits, right? And then here's your field of valid code words. And what you want is the ratio of this to be very small. So, but in another way, you could represent it as this. We have a valid code word, A, a valid code word, B, a valid code word, D, a code word, C, right? And we want to have the ratio, we want to have invalid code words in between them. So imagine we have the valid code words A, B, C, and D. And they're in a field and all the bubbles are touching each other. So like, let's say we receive this code word. If we receive this code word, what is it likely? It's A, right? And if we receive this code word, it's B. Now imagine the bubbles are touching together. This is only 1 bit from here, right? So we could have code words that are evenly distributed in a thought experiment where we could easily decide, and this goes back to our 111,000 example, right? One is it's easily to discern logically, hey, if we land somewhere closest to A, it's A. If we land somewhere closest to B, it's B. And from a binary level, right, these are only 1 bit apart. So if it lands here, it's probably B. If it lands 1 bit further away, it's probably D. So let's actually look at that in practice. In Hamming's paper, he actually described that. So let's say we want to send the data bits we want to send the data bits 0101. So 0101 becomes D, right? So 2D plus 1 is what? That's 7, right? We're going to put 3 check bits right here. So this is going to be data. This is going to be check. And more formally, let's just leave it at that. I don't need to know that. And so what he said is, like, let's do a parity. And instead of doing a parity across this, we're going to do a parity where the parity is scattered. Multiple parity. So our code word is going to be 7 because there's 4 data bits and 3 check bits. And I'm going to do this just going to number them like that in the position that they're in. And I am going any even multiple of 2, so even power of 2, I'm going to reserve that. So this one right here, going to be reserved because 2 to the 0th is 1. This one right here is going to be reserved because 2 to the 1st is 2. And this one right here is going to be reserved because 2 to the 2nd is 4. Now just for right now, I'm going to put zeros in there. And then we lay our data out in the open spaces. Well, conveniently, we have 4 because we designed it that way. So we have 0, 1, 0, 1. Now, I am going to take a parity of all of the even powers of 2. What do I mean by that? Well, if I have 3 parity bits, right? So I have 2 to the 0, 2 to the 1st, and 2 to the 2nd, right? So that actually in binary form is 001, 010, and 100, right? So I'm going to replace that with all the zeros with question marks. Oops. So any number that falls in where it's basically, think the question mark is wildcards, that has that bit set, we are going to take the parity of that number. So let's go through and do it. So in if you take this, right, so that means check bit 1 covers all of this. So what numbers are those? Well, it's 1 for sure. What other numbers? Huh? It's all the odd numbers. And what does P2 equal? Huh? So it's 2 for sure, right? What else? Could be 3, right? 6, it could be 7. Right? And what's P3? Four for sure. What else? 4, 5, 6, and 7. Right? So those are all the 3-bit variations where one particular bit is set. So now here becomes our parity checks. So let's take a look. So we're going to, in position 1, 3, 5, and 7, we're going to take a parity. So in position 1, which is, we'll just call it 0 for right now because it's non-existent. And then 3, 5, and 7. What's our parity? The bit should be 0 for real this time. Right? And the next one? 2, 3, 6, and 7. 2, 3, 6, and 7 is 1. And the next one? 0. For 4, 5, 6, 7? Yep. 0 for real this time. And then we send that code word. And of course, error detection, we can simply make sure that all of them are correct, right? So this works for error detection. We just simply make it wrong as correct. But now I'm going to do something to you. Pick one. Which one do you want? I don't care what position.
5.
5. 5 used to be a 1. We're going to make it a very square 0. And the receiver receives this. Let's go through and calculate the parity for these things. All right. So 1, 3, 5, and 7 becomes what? 1. 2, 3, 6, and 7 becomes what? 0. And 4, 5, 6, and 7 becomes what? 1. Right? Now this is bit 1, right? So let's put that here. And this is bit 2, let's put that there. That's bit 3, let's put that there. What does that number equal? 5. Our error is in position 5. Okay? Want to do it one more time? Or do you just want to take my word that this will always work for one change? So it will always work for one change. So you'll not only find that it's an error because it doesn't equal 0 when it should equal 0. Obviously, there's no position 0 for a reason. 0 is all good. Yay! So if it equals any of these other positions, that means there is a bit in error in that one. So this type of code can correct one error, right? And it can detect up to 2 errors. Of course, if you got 2 errors, then you might find, you would recalculate, and if you try to correct it, it wouldn't work. Right? But you could detect up to 2 errors. Right? So it will allow you to do this. Let's talk about the design of this code. If we actually put the bit stream in here, is there any problems? Because, by the way, it doesn't just need to be 7, right? We can do any 2 to the x minus 1 positions. We can do lots. It can be really big. Right? We're just doing easy math.
The terminator is?
Huh?
You don't know where the terminator is? Like how long that stream is?
Well, presumably, like we have framing, like we talked about last week, and so you know where things start and stop. So we presumably have framing, so we know what the message length is supposed to be. Part of the problem is that it's very heavy, the parity check bits are very heavy on this end. right? They're not evenly mixed, but we can mix them, right? If we said, hey, we're gonna do this with messages of 2 to the 16th minus 1, and just mix the parity bits around in there, right? So that they're evenly dispersed. But we can still only detect one error, right? Or correct one error. We can detect 2. The other thing we haven't talked about is actually using confidence values. So, no need to write this down, mess up your notes, but let's talk about the concept that the physical layer has access to confidence values. Right now, we've just been doing things on the bit level. You receive this bit, you have this string of bits, you have no information on how strong those are. But that's not realistically, you actually do have information if you're designing the network, right? You took an analog reading to determine 1 or 0, you know how strong that reading was and how close to it was. So you could use confidence values, right? This was slightly a 1, it was slightly a 0, right? Or you could say, hey, I have this. Remember, we started out with 0 here, and I'll just ignore this for a minute. We have 1 here, and what we wanted to represent was something like this, right? And then we sent an analog signal across it like this, right? And so you said, hey, this is our middle line. Anything above here was 1, anything below here was 0. Right, but then I introduced noise, right? And it's going all over the place, right? And then, let's say for whatever reason, it got some attenuation also, right? And so now we have this 1 up here, but it's a really weak 1, very small value of 1. So we could use that confidence value and design an algorithm around that, and they do that in what they use that for. One of the main methods of doing that in modern networks is Viterbi. I'm not going to discuss that, but they do that. The other thing they do is a low density parity check. So a low density parity check says, hey, if you get any weak readings, let's just treat it as if it was the question mark. So now we wanted to send something across the internet, and we're going to send the code word Again, you don't need to write any of this down. We're going to send the code word 101011. I'm going to say 011?
Yeah.
011. And I'm going to come up with a scheme. And the scheme is going to do linear transformations, blah, 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 blah. But it can be actually represented as sums of a scattering of numbers. So in this position, we're going to scatter it a lot like Hamming did. So remember, Hamming scattered on powers of 2, right? Whatever bit was going to be flipped. We're going to do somewhat the same thing, and we're going to say, hey, the first 4 numbers exist like this, where all of their sums have to be modulo 2. 0 modulo 2. Right? So again, it's just a parity. And then we're going to have another one, and this one is here, here, and here. And the last one is here, here, and here. Make sure. Yes. And it goes on, right? This is just an excerpt of a very long code word, right? So, because this isn't evenly scattered, because this one has 4 and these have 3, these actually have ones that go off the chart, right? So that we can determine things. Now let's say we have error, and we're going to just kill this one to a question mark. And we're going to kill this one to a question mark. Now looking at it, we've done 2 errors in this thing. And we have just zeroed it out because our reading was super weak. And we're just going to pull this back out. Our reading was super weak. So can we determine any of these? What bit is what? Remember, they all have to sum to 0 modulo 2. You can determine this middle one, and what does it have to be?
0.
Huh? It has to be a 0, right? Because this one's a 1, and this one's a 1, so this one cannot be a 1, right? So we can fix that one. Can we fix that one?
Well, once you fix that one, you can fix
Sure. Yeah, exactly. That's the question. You can't fix it now, right? But if you fix this one, now you can, or 0, right? Now you can fix that one. Right? And so you iterate over it until you fix all the errors. And this is a very simple representation, right? Is doing this with very large matrices and multiplying it out. But so interestingly enough, this was discovered in like 1964 or something like that. A guy wrote his PhD thesis on it, who later became a really famous computer science guy. But nobody used it. Why wouldn't they use it?
Processing time.
Store.
It's processing time. It's 1963. 1963, let's think about what it took to do like a matrix transformation. Right? Even a simple matrix transformation. Take this picture and rotate it on an axis. It might take a day, right, to do a large transformation, right, on punch cards, right? So, and this is actually before real networks also. By the way, we hadn't even talked about networks yet. We're still just talking about data communications. One thing talking to another. We haven't talked about networks yet, right? So, so in 1963, he wrote his PhD thesis on this. Everybody forgot about it. And then in 1996, somebody wrote another paper on that, saying, hey, we have fast computers today. We could actually use this for error correction. And so now it actually is it's used all sorts of places now. But
What was this called again?
huh?
What was this called?
So this is low density pair check, but it's commonly called a Gallagher check because Gallagher's the guy that.
Smashes watermelons?
Huh?
That smashes watermelons?
Yeah, yeah. He's also the guy that smashes watermelons. But when he was getting his PhD, he figured this out. Guy named Robert So then we can actually use, this is one tiny example of how you can use information from the lower level physical layer of being able to measure an analog signal and use that information to come up with error correction schemes. This error detection scheme, by the way, approaches Shannon. And they usually pull back a little bit off Shannon because of the amount of calculation that's needed, but it approaches the theoretical limit. You can actually come up with these sparse matrices to actually do these transformations and approach the theoretical limit for error correction and error detection, for that matter. So now we have error correction and we have error detection. We've discussed both. Why on earth, if we have error correction, do we want to use error detection?
Detection faster.
Detection is often faster, yes. But even let's say it wasn't. Let's say the error detection and correction was the same. So on our simple Hamming code, right, that was the same. You had to calculate every bit anyway, and then you just simply say that's the bit that's wrong.
Sometimes you just want to detect and retransmit it's faster than correct.
Sometimes it might be faster, so let's discover why it might be faster. So there's actually, you can do the math and say, hey, one is faster than the other. The question is detection always faster than correction? Is detecting and retransmitting always faster than correction? Just throw wild guesses out there.
I would think so.
So, in most of the things that we think about, in the networks we think about, the answer turns out to be yes. Because the networks that we think about, the ones that we use traditionally, like wired networks, right, the errors are bursty, right? We talked about having bursty errors, and that actually makes a difference. And the errors are far and few between. So if you have one packet in a million that's an error, because Ethernet is super, super reliable, by the way. If you have one, it is probably better than one in a million. So if you have one in a million that are error, and you're putting all this code in to do error correction, then that's just wasted bandwidth, right? So let's take two examples. We have a 1,000-bit message. $1,000-bit message, and our bit error rate is 1 in 10,000. One in 10,000. So let's take a look at detection versus correction. So on the first example, let's do random errors. So it's 1 in 10,000, and they are truly random. You never know when they're going to pop up, and it's a single bit, truly random error. So if we have a truly random error, and we're sending this 1,000-bit message, how many check bits do we need to fix this for error correction? Let's just do the simple Hamming one. What's the first power of 2 that goes over 1,000? 10. We need about 10 check bits. So in the case of random, because 2 to the 10th is a little bit bigger than the message, right? Then we just need 10 bits for the simple Hamming code. Maybe we can squirm it down to 9 with some of the other neat stuff, right? But we need about 10. So for error detection, if it's truly random, what does everything look like? So what's the minimum, we're gonna do best case scenario here. What is the minimum number of bits you need for error detection? One. We can do simple parity, right? So we need one parity bit to do error detection, but we have to get the message across, right? So how often do we have to retransmit?
1 every 10 times.
1 every 10 times, right? So 1 every 10 times, we're gonna have to send 1,000 more bits, right? So that is 1,000 more bits, 1 out of every 10 times, right? So on average, we need how many bits? 101 on average in our data flow to do detection, right? Turns out in random, we only needed 10, right, to do correction, and detection we needed 101. Correction is actually faster in random. Because remember, every time we add a bit to our data path, right, it's slower, right? This isn't just a quantity of bits, right? Because we're trying to fill our pipe, it makes things slower. So this is for random. Now let's do bursty. So let's say that we do an experiment and we find that, yes, this thing does error, but errors on average come in bursts of 100. So same presumption here, we have the same message size, same bit error rate, but now bursts come in bursts of 100. So in 1,000 messages, how many messages are in error?
10.
Huh?
10?
It's actually 1, possibly 2, right? So we have bursts of 100. So that means in bursts of 100 we have, our bit error rate is the same. So then we have like a packet, right? 100 might be in here because this is a 1K packet, right? And we have the next packet, but it might be here, right? So let's just say 2. So that means that if we make those assumptions, let's look at what correction is. How, if burst comes in, or errors come in bursts of 100, how many bits do you have to dedicate in a 1,000-bit message to make correction work? Remember, CRC could only detect 4, and that was 32 bits. So the answer here is, it's kind of a trick question. I don't know. It might be more than 1,000. You might not be able to make a code that fits in 1,000, that makes correction. Right? It's a lot. But if 100 bits are possibly in error, then at least you're going to need 100 bits and a lot of luck to figure it out. Right? So let's just go with 100. So to correct, right, you need probably greater than 100. And in detection, so remember this way I did worst case scenario, really inefficient algorithm, and best case scenario with parity, right? I'm going to do it the other way around just to demonstrate. So this is best case scenario 100 with a lot of luck, right? And then the next one is let's do real. So if we're going to do detection and we're going to do it for real, let's use CRC32. So how many bits do we need? CRC32 needs 31 bits. Remember, the generator is 32 bits long. So it needs 31 bits for error correction. And how often do we have to retransmit?
Every 100.
Huh?
Every 100, worst case.
Well, so our bit error rate is 1 in 10,000, right? But we have a burst of 100, so it's a max of 2. I'm gonna erase that. But it's still so it's still in bursts of 10,000, right? So at max, you're going to have to retransmit twice in your message, or you're gonna have to retransmit 1,000 over 1,000 times 2. So and this comes from here, right? So on average, you need 33 bits. Because you just need to send 2 out of every 1,000 times. So it turns out that error detection in this case is much faster, because the network was bursty. The error, or not the, we'll talk about bursty networks also. The errors were bursty in the network. So some general assumptions we can make out of that is for error correction is when we're going to have random errors, and the errors are expected. So what are some networks that we may have random errors and the errors are expected? Wi-Fi, CMDA, LTE, right? Anything wireless, awful, right? Because we have this random stuff everywhere. We have random attenuation and everything else, right? So we'll have random errors. What else? There might be another special case. What if you are the guy programming the network for the Mars rover? What's the first of all, what's the round trip time for the Mars rover?
6 minutes.
6 minutes. So is that really? So our delay is 6 minutes, right? Normally we measure delay in milliseconds, and now we're measuring it in minutes, multiples of minutes. Retransmission might not be an option, right? So you might want to build a whole lot of error correction in your transmission. What else? So for error detection, when will we want to do that? Wired networks, and it's usually because the wired networks are extremely reliable. So your probability of error is extremely small. If your probability of error is much greater than your packet size, then, and I mean like many orders of magnitude different than your packet size, then so if you have a packet size of 1,500, which is common, 1,500 bytes, so that is 10,000 bits approximately. So, but your probability of error is 1 in 10 million, right? Then building error correction in there is probably not. Why would you do that, right? So you just retransmit in the event you have an error. So wired networks, because they're super reliable, and also any network where the errors are not random, but are bursty. So notice that if we did this same experiment, thought experiment, and we said it was both random and bursty, right? Then correction is going to work again, right? So bursty networks, bursty errors, And remember, errors may be something physical on the network. The most common error is you're disconnected, right? And so you're going to need to retransmit until you're connected again. So that from a network perspective, where you're only seeing a string of bits, a disconnection looks a whole lot like nothing, right? So you're either getting, if you're doing a voltage network, right, you're getting zeros, a long string of zeros, no signal, right? So that could be an error. And in reality, most networks can tell, modern networks can certainly tell that they've been disconnected, right, from the physical layer. So, random or no time for retransmission for correction for detection is when errors are not expected or they are only bursty. So in practice, correction is heavily used at the physical layer. It's heavily used at the physical layer. Why? You have access to the confidence value. So we talked about a very simple low density parity check. That's used in 802.11, Wi-Fi, digital video, LTE, power line. It's used all sorts of places that has a lot of errors that need to be pulled out because of noise. And error detection is used in the link layer, but not just in the higher level link layers, but in all the layers above it. TCP uses error detection, and that's all the way up in the transport layer. So let's talk about retransmission. If you detect an error, in order to fix it, you got to ask for it to be retransmitted, right? No, or maybe not, because it's 413. We will talk about retransmission next time. It's a clean break anyway. All right.